Let's turn our focus to two-sample testing instead of one-sample testing. The two are very, very similar to each other. We're still going to check claims. We're still going to test data, get samples, and evaluate where it falls in regards to the critical value, in regards to whether we can support or fail to support a claim. Well, in this particular case, instead of looking at one population and a claim specifically made about it, now I might be looking at two different populations. For example, the average house price in one town versus the average house price in the neighboring town, or the percentage of women who do one thing versus the percentage of men who do something else. This is very similar. We're still going to set up the hypotheses the same way. When we talk about the null and the alternative, we know things about those already. The only difference here is instead of using numbers and just mu, we're going to have to use mu1 and mu2, or if it's a proportion, p1 and p2. Because now we're not talking about just one mean, we're talking about a mean for two different areas. So go ahead and think back, what symbol has to go with the null hypothesis? Take a second. Hopefully you thought about the equal sign. Well then what three inequalities go with the alternate hypothesis? Hopefully the other three you thought about, not equal to, less than, and greater than. That isn't going to change here at all. The only difference here is instead of it being, for example, mu equals 100 or mu is less than 15, it's going to end up being something like mu1 equals mu2 versus mu1 less than mu2. It's still going to be the exact same idea, except we're going to have means on both sides in this case. So now let's talk about our formula. We're still going to be looking for a test statistic, and we're still going to be looking for a critical value. The critical value is not changing. You're still going to base all that information right here. Is it a two-sided test, which would be alternate of not equal to? Or is it a one-sided test, whether it be less than or greater than, depending on what side you cut off? This, of course, would be less than. Then we'll talk in a second about Z and T, and that's not going to change from one-sample testing either. But let's go ahead and check out the formula. So here's our formula. Go ahead and pause the video right now and go ahead and write that down for yourself. And the thing is, this is going to be the same formula for a Z or a T. And we'll check that out in 1 second. So go ahead and write this down. So now coming back, let's see where this formula came from. Well, think about our formula before. It basically said, if you take your X bar value and subtract your average. The only difference is now we're looking at subtracting the averages from the two populations. The denominator said take the standard deviation from the sample and divide by the square root of n. Well, as we've talked about a little bit, and I'll review it right now, you can't add deviations together, but you can add variances together. And remember, the relationship between variance and standard deviation is, to get the variance, you would just square the deviation, or vice versa. Well, if I take this, knowing I can't add two deviations together and square it, it's going to end up giving me this idea. Well, that is where that comes from. If you look at this and this, it's just this thing over here written twice. But because adding these two together is going to give me a variance, I don't want variance, I want standard deviation. So I went from deviation to variance by squaring. I go from variance back to deviation by doing square root. Almost think of the Pythagorean theorem almost. So think of this as a Pythagorean theorem of statistics. And this is going to be my test statistic. Now I do the exact same thing I did before. If this is a z-test, I check against my critical value using inverse norm in my calculator. If it's a t-test, I have to use inverse t. Still looking at the exact same thing. Is in the rejection region, is in the fail to reject region. The only thing I have to worry about here is if this is a t-test, how am I going to get my degrees of freedom? When you look for your degrees of freedom, look for your two sample sizes. Take the smaller of the two sample sizes. Subtract 1. That's your degrees of freedom. So you're taking the smaller of the two. Keep in mind all the other rules. when you talk about a t-distribution, if it's going to be a t, that means one of the samples, doesn't have to be both, one of the samples is too small. If you have a sample that's large, 50 people, versus a sample of 12 people, you have to err on the side of caution and use the t-distribution in that case. Besides that, all the rules stay the same. You're still going to reject and fail to reject the exact same way you did before. Why don't you pause the video now, stop the video, and go ahead and check out some of the examples.